Welcome everyone. I am Subhashish Chandra and we are going to learn digital electronics. Now, as we all know that we live in a digital world, we are surrounded by various digital devices and at the very heart of these digital devices is a logic gate. Now, let's see what a logic gate is. A logic gate is made up of two words, logic and gate. What does the word logic means? The word logic means reasoning, that you give an argument and you get an output out of it. And a gate is basically a door. So a logic gate is a door which works on some kind of a reasoning. So we'll see what these electronic doors do. There are three kind of electronic doors which are called the basic electronic doors: the AND, the OR and the NOT. We'll start with NOT. In case of a NOT gate, what we have used is a transistor T, of which the emitter is connected to ground, the collector is connected to a power supply plus VCC, and the base is connected to an input terminal A. The boolean 0 and 1 have been represented by 0 volt and plus VCC respectively. So A equal to 1 means we are applying plus VCC, and if A equals to 0, we are applying 0 volt. The A will act as the input terminal which will control the transistor gate T. So in the first case, we apply A equals to 1, that is we apply VCC to the transistor T. The base emitter voltage VB is more than the cut-in voltage of the base emitter terminal of the transistor T, and hence this terminal becomes saturated and the entire collector current passes through it, and hence there is no voltage drop at Y and we get Y equals to 0. Whereas in the second case, when A equal to 0, the transistor T is cut off at the base emitter voltage and the entire collector current falls on the load resistance RL, and we get output Y equals to VCC, and therefore Y equals to 1. So we get two cases: when A equals to 0, Y equals to 1; when A equals to 1, Y equals to 0. This is basically a truth table for the NOT gate. The symbol for the NOT gate is shown on the left side of the slide, and the Boolean expression is written as Y equals to A complement with a bar put on over A. This is the most basic gate and it has only one input and one output, and it is read as the complement or inversion of the input. So that is, when input is low, the output is high, and vice versa. We will move on to the next gate, the OR gate. If we see an electrical analog of the OR gate, we can see that both the transistors T1 and T2 are connected in parallel in between VCC and the ground, where here the output is taken from the emitter terminal. When the inputs A and B both are 0, both the transistors T1 and T2 are cut off and we get no output at the emitter terminal, and hence Y equal to 0. When A equal to 0, the transistor T1 is cut off, and B equal to 1, the transistor T2 is saturated, and hence the current flows through the transistor T2 from VCC to ground, and we get an output at terminal Y equals to 1. In the next case, when A equals to 1, the transistor T1 is saturated, and B equal to 0, the transistor T2 is cut off. Again we get output at Y equals to 1. In the last case, when A is also 1, B is also 1, both the transistors are saturated, and we again get output at terminal Y. We can summarize them as: when A equal to 0, B equal to 0, Y equal to 0, and when either of them or both of them are 1, Y equals to 1. So the output of an OR gate is high when any one of the input to the gate is high. It is low only when all the inputs are low. The symbol is on the left side of the slide, and it is represented as Y equals to A plus B, or in this case we will read it as Y equals to A or B. The next and the last basic gate is the AND gate. Again, if we look for an electrical analog, both the transistors T1 and T2 are connected in series. When A equal to 0 and B equal to 0, both the transistors T1 and T2 are cut off, and there is no output voltage at the emitter terminal, and hence the output Y equals to 0. Now, when A equal to 0, B equal to 1, transistor T1 is cut off and T2 is saturated, hence there is no current IE1, and hence the output at RE is 0, so Y equals to 0. When A equals to 1, B equals to 0, The transistor T1 is saturated and transistor T2 is cut off, but there is no current at the RE, and we get Y equals to 0 when both the transistors are saturated. Because of A1 equal to 1 and B equal to 1, the output voltage is obtained as there is current through the resistor. This can be summarized as when either of A or B is 0 or both are 0, the output is 0. Whereas when both of them are 1, the output is 1. So the output of an AND gate is high only when all the inputs to the gate are high. The output is low if any one of the inputs is low. The symbol is on the left side of the slide. It is represented as Y equals to A dot B, or in this case we will read it as Y equals to A and B. Next we will move on to the derived gates. Using these three basic gates we can derive two gates. First is the NAND gate, in which an inverter is connected to the output of the AND gate. Now as we can see from the truth table, when both the inputs are 0, the output is shown as 1, as for both the input as 0, the output of an AND gate is 0 and its complement is 1. Similar for 0 1, the output will be 1, 1 0, the output will be 1, and 1 1, the output will be 0. So the output of a NAND gate is low only when all the inputs to the gates are high. The output is high if any one of the gates is low. The symbol is basically a AND gate with a circle in the front of it. The Boolean expression is the complement of A and B. The next gate that we will see is the NOR gate. To derive a NOR gate, an inverter is connected to the output of an OR gate. And when the inputs are 0 and 0, the output is 1. As we know that for input 0 and 0, the output of a OR gate will be 0 and its complement is 1. Similarly, for 0 1 it's 0, for 1 0 it's 0, for 1 1 it's 0. So the output of an OR gate is low when any one of the input to the gate is high. The output is high only when all the inputs are low. The symbol of a NOR gate is basically a circle in front of an OR gate. The Boolean expression is the complement of A or B. Now for all the gates that we have seen, the NOT gate had one input and the rest of the four gates had two inputs and one output. The NOT gate always has one input and one output, but in case of the other four gates, it can have more than two inputs as well. The output will remain as one. Now we will see two special gates. One is the EXOR gate and other is the XNOR gate. Now the EXOR gate is a derived gate. It can have two or more inputs and one output. We have chosen a two input EXOR gate. In this gate we can see a combination of NOT gates, AND gate and OR gate. So the input A is given to the upper AND gate through an inverter, whereas it is given directly to the lower AND gate. The input B is given to the upper AND gate directly and to the lower AND gate through an inverter. The outputs of the AND gate is given to the OR gate and the output is taken from the output of the OR gate. So if we see the truth table, when both the inputs are 0 or when both the inputs are 1, we get output to be 0, and when both the inputs are different, we get the output to be 1. This is the classical definition for the EXOR gate, a two input EXOR gate. But the general definition is the output of an EXOR gate is high when an odd number of the inputs to the gate is high. The symbol is shown on the left side of the slide and it is represented by Y equals to A XOR B. Now we will move on to the next special gate, the XNOR gate. The XNOR gate is basically a complement of the EXOR gate. In this case, the output of an XNOR gate is low when an odd number of the inputs to the gate is high. Next, we will move to two important theorems of Boolean algebra. They are called the De Morgan's theorem. The first De Morgan's theorem states that the complement of OR equals the AND of the complements. That is, the complement of an OR gate is equal to the AND of the complements of A and B. The left side gate is the NOR gate, and the output truth table is given over there. The second, in which two bubbles are put in behind the AND gate, is called the bubbled AND gate. It is basically two NOT gates are connected to the inputs of the AND gate. So the AND gate in this case receives the inputs as complement of A and complement of B, and when we see the output, we find out from both the truth tables that they are same, and hence this proves the first De Morgan's theorem. Moving on to the next De Morgan's theorem, the second De Morgan's theorem, this states that the complement of AND equals the OR of the complement. Hence, if we see the NAND gate can be equated using a bubbled OR gate, that is OR gate with complemented inputs. So if we compare both the truth tables, we find out that they are same, and this proves the second De Morgan's theorem. Now we'll move on to a thing called universal building blocks. The NAND gate and the NOR gate are called universal building blocks because all other gates can be derived using these gates. So you can use a NAND gate to create a NOT gate, an AND gate, and an OR gate, and a NOR gate can be used to create a NOT gate, AND gate, and an OR gate. First, let us see that how NAND gate is used. If both the inputs of a NAND gate are joined together, so this will effectively act as one single input. The output in this case is the complement of A, and hence a NAND gate can be used as NOT gate. In case of an AND gate, what we have done is we have taken the output of a NAND gate and put it to a NAND gate for which the inputs are joined together. So if you see the Boolean expression, that it is the complement of A dot B, and hence we get A dot B or A and B. In case of an OR gate from a NAND gate, the shorted A, or that is A joined together, is given as one input, A bar, and B joined together is given as B bar. The output over there you can see is the complement of the AND of complements of A and complement of B. Using simple Boolean algebra, it can be represented as the complement of A complement or complement of B complement, and complements of complements is the original itself, so it can be represented as A or B. So in this way, NAND gate can be used to create a NOT gate, an AND gate, and an OR gate. Let's see how we do it with NOR gates. In case of NOR gate can be created as it is shown on the top left, OR gate on the right top, and the left bottom you can see the AND gate. The scheme is same as it was before, and these two gates are called the universal building block, as they can be used to derive any basic gates, and these are the gates which are used to create a different kind of electronic circuits. Now in the last 14 slides we have learned what a logic gate is. We have seen how logic gate can be created using transistors. Then we have derived different logic gates using the basic logic gates. We have seen two special logic gates. We have seen the first and the second De Morgan's theorem. We have also seen that how NOR gate and NAND gate can be used to create the basic AND, OR, and NOT gate. And that's all for now today. That is all about logic gates. I hope the content will be of use to you. Thank you.